These are examples for section 13.4, perimeter and area dimensional changes. Example 1. How does multiplying each dimension of the isosceles trapezoid pictured by a scale factor of 2 affect its perimeter? So K is 2, or 2 over 1, as a scale factor. The first thing you do is find the perimeter of the original figure, which means we're going to add all the sides up. We're not going to ignore the 4. And so 11 plus these 3 sides, of course they're all 5, so we can be smart about it. The perimeter is 3 times one of these sides, so 3 times 5 centimeters, plus this right here, the base, 11 centimeters. So we find the perimeter. 3 times 5 centimeters is 15 centimeters plus 11 centimeters. So the perimeter then is 26 centimeters. The next thing we do is we recalculate the perimeter, but we use K equal 2, our scale factor. So what we can do for our new perimeter, perimeter prime, P prime, is we can take this exact same formula we used, except everywhere we see the dimensions of 5 and 11, we're going to multiply that by 2. So we'd write 3 times 5 centimeters times 2 plus 11 centimeters times 2. So we have the times 2 for both of these. So P prime would be 3 times 5 centimeters times 2 is 10 centimeters, plus 11 centimeters times 2 is 22 centimeters. So P prime, the new perimeter, is 3 times 10 centimeters, or 30 centimeters, plus 22 centimeters. So P prime, the new perimeter, is 30 centimeters plus 22 centimeters, gives us 52 centimeters. Then we take the original perimeter and P prime, the new perimeter, after applying the scale factor of 2, and we determine the new factor of change. That's P prime over P. So we take P prime, 52 centimeters, over P, which is 26 centimeters. Notice the centimeters divide out, and we get 52 to 26. 26 goes into 52 2 times. 26 goes into 26 1 time. So we get a perimeter factor of 2 to 1. And what we need to notice is the scale factor changing each dimension was exactly the same as the perimeter, the change in the perimeter, 2 to 1. It hasn't changed. 2 to 1 is still 2 to 1. So we can conclude that when we have a scale factor, we take the top and bottom numbers and we simply take them to the first power, and we still get a to the first over b, or a over b. We still get k. This is called the perimeter ratio, PR. So the perimeter ratio is the same as the scale factor. Example 2. Now this time we're going to take the same exact figure. This time we're going to see what happens to the area when we apply the exact same factor. How does multiplying each dimension of the isosceles trapezoid pictured by a scale factor of 2, just like before, and then we'll figure it out what it is with 3 later. How does it affect its area? So begin again. You start with finding the area first of the original figure, and this is a trapezoid, isosceles trapezoid, so that's 1/2 times the height times b1 plus b2. So substituting in our dimensions, we have 1/2 times the height, which is 4, times b1, I'll use 11 centimeters, plus b2, which is 5 centimeters, and determine the area. Half of 4 is 2, or 2 goes into 2 once, 2 goes into 4 twice. So we have 2 times 11 plus 5 is 16. So our area, 2 times 16 is 32 square centimeters. Now at this point we recalculate the area, but this time we take all the dimensions 4, 11, and 5 and we multiply each one of them by 2 like so. A prime, the new area, is 1/2 times 4 centimeters times 2 times B1, which was 11 times 2, plus B2, which was 5, but we're going to multiply it with 2. So we multiply 2 with each and every dimension. Height, base 1, base 2. And then we work this out. This is 1/2 times 4 times 2 is 8 times 11 times 2 is 22 plus 5 times 2 is 10. Then we have half of 8, or 2 goes into 2 once, 2 goes into 8 4 times. We get 4 times 22 plus 10 is 32. Finally, 4 times 32, we get 128 square centimeters. Again, to determine the change, the factor of change, or the change factor, we take A prime this time over A. Last time we took P prime over P. And so this would be 128, our new area, centimeters squared, over the original area, 32 square centimeters. Square centimeters both divide out, we get 128 to 32. And 128 32nds does reduce by 32. 32 goes into 32 once. 32 goes into 128 4 times. So we get a factor change of 4 to 1 for our area. Even though we used a scale factor of 2 for our dimension, our area is 4 to 1. This is our area ratio, AR. So we can look at a pattern here and notice a pattern and draw a conclusion. What happens is K, which is A to B, is being squared. And so A squared over B squared is actually the area ratio. So what you do is you square the 2 and you square the 1. 2 squared is 4, 1 squared is 1. And this is the area ratio. How does this trapezoid differ when all the dimensions have been affected by a factor of 3? Instead of going through all this, what we can do is we can take 3 to 1 instead of 2 to 1, like this was. And knowing what we know now, we can square the scale factor. 3 squared over 1 squared. This gives us 9 to 1. This means that the area of the figure that's 3 times bigger is going to be actually 9 times bigger in its area. What we could do is we could take their original area and multiply by 9 instead of by 4, like it was done here. Example 3. The trapezoids below are similar. Remember, similar figures means that all the corresponding sides are proportional. Similar figures. And they give us this side right here, the upper side of this trapezoid corresponds to the upper side of this trapezoid, since they're similar, and therefore these two are corresponding sides. So we immediately have a scale factor of 6 to 9, or we can reduce that to 2 to 3. So K is 2 to 3, and they want to know A, what is the perimeter ratio? So if we were to find the perimeter using the scale factor from one to the other, we would take K, which is 2 to 3, and we would take both the numerator and denominator and take both of them to the first power, which of course would give us 2 to 3 again. This is the perimeter ratio, and it's what we would use to find the new perimeter using this scale factor. part B. What is the area ratio? So again, we start with these two figures that are similar, 6 to 9, corresponding. 2 to 3, they reduce to. We take K. This time we square it, as we discussed before. So we take 2 to 3, and we square both numbers or terms in the scale factor. 2 squared is 4, 3 squared is 9, and so 4 to 9, or 4/9, is our area ratio. That means the area of, using this scale factor, the area of this one is this many times larger. Example 4. The area of the smaller regular pentagon is about 27.5 square centimeters. So we know the area of the smaller one right here is 27.5 centimeters squared. And they're asking approximate the area of the similar, larger regular pentagon. Instead of having to find the area completely from scratch here using the Potham and doing all that, we can now, since we can find the ratio or scale factor between these two, these are corresponding sides, we can come up with a scale factor, use the scale factor and the area of the smaller one to find the area of the larger one. So it cuts out quite a few steps and a lot of time if you have this information. So the first thing we do is we determine the area ratio from using corresponding sides beginning with K. So let's find K first. Take a look at the two figures, and we have 4 centimeters to 10 centimeters. And then we simplify as much as we can. The centimeters divide out, we get 4 to 10, and that reduces by 2. So we get 2 to 5. This is K. This is our scale factor of small to large. Now we're going to use this and find our, next thing we do is find our area ratio. You have to find the area ratio if you're going to find the new area first, to find the area ratio. So we take 2 to 5, and we square both of them, 2 and 5. That gives us 4 to 25. This is our area ratio. Then we take the area ratio and set up a proportion. 4 is to 25 as, and then now since it's the area, it represents the area, we now take the areas. This area, the smaller one, is 27.5. So since the smaller one is in the first term and not in the second term, this is smaller than this one, we put the smaller area up here in the numerator, 27.5 square centimeters. And we're looking for the area of the larger one, so I'm going to call it its area. I'm going to use A for area in square centimeters. So A square centimeters. You can use X or whatever variable you want. Now we simply cross multiply. 4 times A is 4A. And 25 times 27.5 is 687.5. Solving for A, divide both sides by 4. And the area of this larger figure, all of a sudden we find it, is 171.9 square centimeters. This is the area of the larger pentagon. Example 5. Agriculture. During the summer, a group of high school students cultivated a plot of city land and harvested 13 bushels of vegetables that they donated to a food pantry. Next summer, the city will let them use a larger, similar plot of land. So here's our original plot that they got 13 bushels out of. And next summer, the city is going to let them use a similar, larger plot right here. In the new plot, each dimension is 2.5 times its corresponding dimension of the original plot. So since all the dimensions are changing in the same way as with a factor, we can use our little factor rules for area and perimeter ratios. We want to know how many bushels can be yielded out of this new plot of land. The first thing we do is we take a look at the area of the original plot, and we equate it to how many bushels you can get. So the original plot will yield 13 bushels, therefore we're going to set the area of that original plot to 13 bushels. Keep that in mind. Then we need to determine a scale factor. So what we can do, since both dimensions are 2.5 times larger than these, we can simply use the scale factor 2.5 to 1. Remember, if the top number is larger than the bottom one, you're getting larger, and we're getting larger. If we were getting smaller, we'd use 1 over 2.5. Anyway, this one's getting 2.5 times larger in both its dimensions, so we use this K. Second, we find the area ratio. So to find the area ratio, we take K and we square it. So we're going to square 2.5 over 1. Well, that means we square 2.5 and we square 1. 2.5 squared is 6.25, and 1 squared, of course, is still 1. So this is our area ratio that we're going to use. To find out how many bushels this will put out, we equated the area of the original plot with the number of bushels. So we can set up a proportion now using our area ratio. 6.25 is to 1 as the area of the larger plot, which we don't know yet. I'll call it B for bushels. B bushels. How many bushels can be yielded, over the number of bushels that yielded for the smaller plot. And then we cross multiply. 1 times B is 1B or B. And 6.25 times 13 gives us 81.25 bushels. So, or therefore, the new plot will yield over 81 bushels of vegetables. Example 6. The triangles shown are similar. What is the scale factor? So we need to find the scale factor first. So we're going from area, and we're going to go find the scale factor. So far we've always gone from the scale factor and gone to area. To do that, we squared the K to get the area ratio. Here we're going backwards, so the inverse operation of squaring is to take the square root. So if we have the area ratio, then it's going to be the square root of K. Or excuse me, the square root of AR will give us K. So, first thing we do is determine the area ratio. So they give us the areas. That should be fairly simple. So we determine the area ratio by taking the areas themselves. So directly we have 50 square centimeters to 98 square centimeters. Now let's simplify before we try to take the square root. That's that's always a thing to watch for, because if you don't simplify, sometimes it can cause you a whole bunch of work that you don't need to do. The centimeters squared cancel out and we get 50 over 98. Well, if you try to take the square root of these, you can do it, but 50 and 98 are perfect squares. So let's see if we can reduce that first. We can reduce that by 2, and we get 25 over 49. And if you'll notice, 25 and 49 happen to be perfect squares. So the next thing we do, we've got our AR, our area ratio, right here. We take that area ratio, and to find the scale factor, we take that square root of it. So we take area ratio, square root of it. Area ratio is 25 to 49. Take the square root, which means we take the square root of the numerator and take the square root of the denominator of the ratio. That gives us 5 to 7. This is K, our scale factor now. each dimension from this one to this one is 5 to 7. Now that we have 5 to 7, this is our first answer. They want to know also what the perimeter ratio is. We don't go back to the area ratio, we use the scale factor. We're going to take the scale factor and we want to find the perimeter ratio. As you recall, you take the scale factor K and you take both the numerator and denominator to the first power, and of course that gives you the same thing, 5 to 7. So 5 to 7 is the perimeter ratio. So there's the second answer. They both were the same. All the previous examples were based on proportional change. So this is why we could use the scale factor on each and every one of them. Now we're going to discuss non-proportional change. With non-proportional change problems, you can't rely on any of the patterns that we just talked about. You have to take each problem and read it, and you may be adding something to one dimension and multiplying something to another, so you just have to take it piece by piece. So example 7, the botany club plans to increase the size of a rectangular garden by adding 8 feet to each dimension of the garden. At first that seems like, well, that's proportional change, but it's not proportional unless we multiply by the same number. So this is non-proportional. They want to put fencing around the proposed garden. How many more feet of fencing will the club need to buy for the new garden than it would have bought for the current garden? So the first thing we need to do is find the perimeter of the original garden. Since this is a rectangle, we can use the old formula 2 times the length plus 2 times the width, or you can just add them all up if you want. And so our length, I'm going to use a length of 22 and my width is 16. So finding our perimeter, this would be 2 times the length, which is 22 feet, and plus 2 times the width, which is 16 feet. And then working this out, 2 times 22 is 44, plus 2 times 16 is 32. And so the perimeter of this original garden then would be 76 feet. So we find that first. We need a baseline there. Remember, they're asking how many more feet of fencing, so we need to know how much fencing there was originally. Now we come over and we find P prime, or our new perimeter, and it said we're adding 8 feet to both dimensions. So everywhere we see L and W, we're going to add 8 to it. So this would be 2 times L plus 8 plus 2 times W plus 8. So now we plug in our original length and width here and here, and we have 2 times 22 is our original length plus 8, plus 2 times our original width was 16 plus 8. So P prime is equal to, use the order of operations, 2 times 22 plus 8 is 30, plus 2 times 16 plus 8 is 24. P prime is 2 times 30, which is 60, plus 2 times 24, which is 48. We add those up, we get our new perimeter after adding 8 feet to both the length and the width is 108 feet. Now, one more step, they want to know how many more feet, how many more. That implies we need to subtract and find the difference. So we take P prime and subtract P. We have 108 feet minus 76 feet, and that gives us 32 feet more in fencing. So they're going to need 32 more feet after they increase the size of the garden. Example 8, another non-proportional problem. The botany club, mentioned in example 7, the one we just did, wants to cover the proposed garden with a layer of mulch. how much greater is the area of the proposed garden than the area of the current garden. So this time we're doing the same type of thing, except dealing with area. And when you spread out mulch, you're going to spread it out all over the garden. That's the surface of that rectangle, so it's area. They want to know how much greater, so we're going to end up finding the difference between those two areas. So let's start off with our original area. A equals, since it's a parallelogram, specifically a rectangle, we can use base times height. Our base, I'm going to use the base of 22, and my height is 16. Or you can switch it around and use 16 for base and 22 height, but I'm going to use 22 for my height. So area is the base, 22 feet, times the height, which is 16. So we find our area, multiplying 22 times 16, we get 352 square feet. Then we apply the change that they're mentioning up here, being very careful to make sure we do it correctly. We take the original formula, except now it's A prime. We take B and H, except we're going to add 8 to both of those, just like we did last time. So we have B plus 8, and then we take our H, multiply it with H plus 8. We substitute in our B and our H. Our original B was 22 plus 8 times our original H was 16 plus 8. So A prime, or our new area, using the order of operations, we need to do what's in parentheses first. So 22 plus 8 is 30 times 16 plus 8 is 24. We multiply those together, and A prime now is 720 square feet. Now again, they want to know how much greater will the area be. They didn't say how many times bigger the area would be. They asked how much greater, so we're going to use subtraction. A prime minus A. So we take 720 square feet and we subtract from it 352 square feet, and we get 368 square feet more in area for the mulch.